I will talk about performance evaluation of FPGAs. So in our paper, we proposed a new benchmark suite, which I hope will become useful performance measurement tool for FPGAs in the context of high performance computing. So what we exactly did, so we implemented an FPGA adapted version of the HPC Challenge benchmark suite. So the main features are, first of all, that we implemented the benchmark kernels in OpenCL. So this means that we also do not only want to measure the pure hardware performance of the FPGA boards, but also want to measure the tools that are needed to actually synthesize the kernels, in that case for OpenCL. We want to support a broad range of recent high-end FPGA boards that are used in HPC. So that means that we want to support Intel and Xilinx FPGAs actually with the same kernel code. Also, we provide configuration options for every benchmark kernel to adapt to the resources and architectures of the FPGA, so to allow decent performance also on a broad range of devices. And last but not least, it's already available and published as open source on GitHub, so you can already use it and yeah, maybe also contribute. So maybe let's first of all dig into the HPC Challenge benchmark suite for CPU. So it contains 7 benchmarks. So we have 3 synthetic benchmarks that measure the pure memory bandwidth and network bandwidth. And we have 4 benchmark applications. So we have a matrix multiplication, a parallel matrix transposition, an FFT, and high performance LinPack. So these benchmarks were chosen to represent extreme cases in spatial locality and temporal locality of memory accesses. So all other applications will be located, if you look at this figure, somewhere within this rectangle here. Maybe to give an example, so if we look at stream, we have very low temporal locality because we will execute vector operations. So we will just use every data item in the data array once, whereas we have a high spatial locality because we will always access subsequent values in the array. Yeah, so of course, memory accesses play an important role in getting overall performance for an application. So this is why these benchmarks and this setup was picked for the benchmark suite. Another important point is that we have a strict separation between base runs and optimized runs. So in base runs, the rules are that unmodified benchmarks that are contained in the benchmark suite should be executed without modifications, as said. And in optimized runs, it's also allowed to actually modify, in our case now, the kernel code to achieve better results. So in the current step, we will focus on the base implementations just to cover a broad range of FPGA devices and not focus too much on getting the best result possible for every FPGA. So to summarize goals of this work, so first of all, we focus now on the execution on a single FPGA, and we really focus on the FPGA board itself for executing our benchmarks. So the only relevant metric here should really be the execution of the benchmarks on the FPGA. So we implemented in the first step 4 of the 7 benchmarks and provided configurable-based implementations for them, which are stream, RandomAccess, FFT, and the matrix multiplication. So this means we cover actually every edge of this rectangle here. So our goal was now to actually create benchmark kernels that provide comparable performance efficiency in terms of, for example, models for the problem, or also in terms of hardware limitations. Another aspect was that we actually utilize the application relevant resources on the FPGA to a decent amount. And as already said, so we want to support Intel and Xilinx FPGAs with this benchmark suite. So I talked about the base implementations and the configuration options. For the configuration options, we also follow 2 different approaches. So first of all, we want to enable the user to scale the benchmark kernel. So that means if we have an FPGA here, and let's say these red thingies here are memory banks of global memory, then one thing that we want to do is we want to scale for example, the load and store units of the kernel to match the preferred width of the global memory interface. Another thing we would like to scale maybe, for example, the parallelism of the calculation so that we can actually make use of more resources on the FPGA itself and also gain performance. But now there may be problems or applications that work best, for example, by just using a single memory bank. So to further increase the performance to the resource utilization of the FPGA, and with that the overall performance of the application, is to create replications of the benchmark kernels. So before we had now one kernel that may efficiently use one memory bank. Now we replicate the kernel, so actually create an exact copy to also utilize the second memory bank. This does not necessarily mean that these both kernels work on different problems now, so we may also just split the problem now between the kernels to calculate it faster. So for our evaluation setup, we used 3 different FPGA boards that are listed here. I now listed the used FPGAs on the boards and the global memory because this will be actually the most important part when executing the benchmarks currently. So the first boards, the 520N and the PEC board, have a quite similar Stratix 10 FPGA equipped, but we use different global memory here. So the 520N has 4 banks of DDR memory, whereas the PEC board, for the PEC board, we used a reference board support package that allowed us to directly access the host memory from the FPGA board. Additionally, we have a Xilinx FPGA, the U280, which also comes with 2 different kinds of global memory. So we have 32 banks of high bandwidth memory, HBM2, and also 2 banks of DDR memory. So maybe to get an impression how this all works together. So with our benchmarks, we now, when we talk about memory, we talk about the global memory that we use in the FPGA. And again, we have the high bandwidth memory that is most often located directly on the FPGA fabric. We have the DDR memory, so I will call it DDR memory in the presentation, which is the DDR memory located on the FPGA board. And we have shared virtual memory, which means that we actually access the host DDR memory over the PCI Express connection between host and FPGA board. Yeah, so let's look into the actual benchmark implementations. So I want to now give you a short impression of all the 4 benchmarks that we implemented, and also some further insights for every benchmark. So let's start with Stream. So as already said, Stream is a synthetic benchmark that aims on measuring the global, in our case now, the global memory bandwidth of the FPGA. For that, it uses different vector operations that are executed and listed here in the table. Now, for our implementation, we concentrated first on a single global memory bank. So you see the bank here below, and you see 3 input buffers in 1, in 2, and out. And what we were trying to do, we implemented a kernel that actually can execute all these 4 operations, copy, scale, add, and try it, by just changing the input parameters of the kernel. So how does it work? So if we look at the copy and the scale kernel, for that we have a first pipeline that will load data items from the global memory and scale them with a value that you can give as a kernel parameter, and then store it in the local memory buffer. So this will be the first pipeline. And by setting scalar value accordingly, we can do both operations here. So the second pipeline that will be executed after this pipeline is optionally. And with that, we can actually do the add and triad operation. So we again just load from a different buffer and global memory data items and add them to the data in the local memory buffer. And the third pipeline will just write back the data from the local memory to the global memory. Yeah, so we will have these three separate pipelines, and every pipeline will just have a single access to global memory. Now we have configuration options for these benchmarks. So first of all, we want to define the width of the load and store units that we use to load data from the global memory and also to store in local memory. And we can do that by actually defining the data type that is used for this benchmark. So we can not only decide between the half, double, and single precision, but we can also use OpenCL vector data types here. So these are the two configuration options that I use for this. Additionally, we can also partially unroll this loop here to further widen the load and store units. Another configuration option is the device buffer size. So this defines the size of a local memory buffer. So the bigger the buffer is, the longer the pipelines can actually run until the buffer is full and the next pipeline has to start. And the last configuration option is actually the number of kernel replications. So as already said, so here we will just use a single memory bank. If we have an FPGA with multiple memory banks, then if we remember back the FPGA figure from before, we will just actually split the arrays between the available memory banks and yeah, replicate the kernel for every memory bank. Okay, let's look into some performance results here. This figure shows the memory efficiency of all the stream operations. So with memory efficiency, I mean the bandwidth that was actually measured by the benchmark and the bandwidth that is the theoretical peak according to the hardware specification. So here we see that actually Stream achieves quite high memory efficiency for the boards using DDR memory and high bandwidth memory, independent of the operation. So for copy, scale, add, and triad. What we can also see is that for the PAC board, so by the way, the efficiency here is a little bit lower because we also have to consider that the shared virtual memory will be accessed over the PCI Express connection, which also comes with the protocol overhead. So we can see here that there's actually a difference between the add and the triad and the copy and scale. And this is because of the imbalance of the input and output data. So this actually reduces performance in SVM because PCI Express supports full duplex, so we can simultaneously read data from the global memory and write it back. But the bandwidth for the read and the write channel is actually fixed. So what happens here with add and triad is that we cannot fully utilize the write channel actually. Okay, so up to the next benchmark. In RandomAccess, we want to update values in a very big data array in a pseudo-random order. The interesting thing here is that update arrows are actually allowed. So you don't need to do every update correctly. So initially we have a similar setup than for the stream benchmark. We also have a local memory buffer here, and we also replicate the kernel for every memory bank we have. So now basically we split this benchmark also in two different pipelines. So the first pipeline will read values in pseudo-random order from this global, for this data array located in global memory and stored in the local memory buffer. And then we will have a second pipeline that just writes back, first updates the values in the local memory buffer and then writes them back on their previous location in the global memory buffer. So this is actually done to remove the data dependency that we would have if we would execute this operation in the same pipeline. So because we do it in a pseudo-random order, we don't know if we might load maybe the same item 2 times after each other. So most likely the compiler may create a single pipeline, but this pipeline will most likely stall all the time because it has to wait until the data is actually completely updated and back in global memory. So this local memory buffer prevents this to some degree by just storing multiple reads in the local memory, and then so if we look at the results here, so you can see in this table the total performance results, mega updates operations per second. This is the metric that is used for the random access benchmark. You can see that the 520N board actually had the by far highest performance. And this is actually because we could use a nice trick here. So for the Intel compiler, there's the possibility to actually tell the compiler that we don't want to consider this memory dependency. And with that, we could actually create this single pipeline and reduce the stalls there. For all the others, you can see that the error is actually exactly the same. This is because we picked the same memory buffer size here for every benchmark, for every implementation. And this is also some interesting thing now of this implementation. We actually can define the error that this benchmark will create in the end by defining the buffer size. And this actually also helps to achieve validating this design for every FPGA, because with the pragma call, we can actually not be sure if this will create an error below the threshold of 1% or not. Okay, so let's be a little bit faster with FFT. So the FFT benchmark so in the FFT benchmark, we calculate the batched 1D FFT. So here we actually fix the size that the FFTs will use. So let's say maybe 2 GB of FFTs are calculated. So here we have a fully pipelined implementation. So we read the FFTs from one memory bank, apply the FFT in the pipeline, and then write it back to another memory bank. So this whole implementation is based on an inter-reference implementation. Right, so with this benchmark, it is now, since it's fully pipelined, it's possible to also utilize the global memory to a high degree, but also to use the FPGA resources because we do actual calculations. So here in the FFT kernel, the FFT stages will actually be unrolled. So the bigger we choose an FFT, the more DSPs will be used and the more calculations will be done in parallel. So as configuration options, we have the FFT size and also the number of kernel replications. So if we look at a rough performance model, so since this is fully pipelined, if we want to now have a guess how many flops per second we can get here, we can actually use this formula here, and you already see that the FFT size and the number of replications actually have the same impact on the final performance. So what we can, first of all, what we'd see now when we evaluate this FFT benchmark is that we also get a high global memory bandwidth efficiency here, actually independent of the FFT size we used. So we have quite big FFT sizes here and a small one for the board using high bandwidth memory. Also, we are able to partially compensate a lower global memory bandwidth by just increasing the FFT size. You can see that just here in the configuration options. So here actually shows for the 500N board with just 4 memory banks, much larger FFT size to just utilize more resources here. In interest of time, I will skip gem now, and yeah, just directly come to the conclusion. So first of all, what you may have understood now is that it's a challenging task to actually create, first of all, unbiased implementations for Intel and Xilinx FPGAs, because most of the time implementation may come from one direction or the other, and the code is actually interpreted in very different ways by the compiler. But what you could now see with the benchmarks I've shown, that they actually show similar performance efficiency for the tested devices. So, and yeah, and what we can see actually now, what we can do with it now is that we can actually show the some of the performance characteristics of the FPGA already with the benchmarks we currently have here. So if you look at this radar plot you shortly saw at the very beginning, you can see, so this radar plot contains the normalized values of the benchmark execution and on all these 4 device global memory combinations. And so for the stream benchmarks, add, scale, add, try, scale, add, and copy, you see that the board with the HBM memory achieves quite high memory bandwidth, so that was expected. But for example, for the matrix multiplication, we can see that the memory bandwidth actually does not have that much impact on the performance, but it may be rather something like what kind of DSPs are used in the FPGA or how many DSPs. So here the HBM, for example, is not has not the best performance. And for FFT again, the global memory bandwidth plays an important role. So we see that here again with the HBM board, but it's not the only important thing. So we see that the 520N board is actually better compared to the difference we see in the stream benchmark. And last but not least, also for the random access, we see that compiler options or compiler features may also allow to achieve way better performance than it would be maybe expected by looking at the pure memory bandwidth. Yeah, so the code is available on GitHub, and all total benchmark results and resource utilizations are also given in the paper. So yeah, thank you for your attention.
Yeah, thank you very much, Marius, for the interesting talk. We already have a question by Arthur. He says, thanks for a nice presentation. For the stream, for the copy benchmark, his question is how much better do you think a DMA IP would transfer the data compared to the high-level synthesis version?
So I have no experience with other approaches there actually. So I think I can't give a meaningful opinion there.
Okay. Any further questions? Okay, well, while we are waiting for more questions, I found myself. So, from your experiments, did you learn anything about like both Xilinx and Intel FPGAs are not designed to accelerate general high-performance computing workloads? Have you learned anything what is missing from these architectures, or do you think a different mix of resources from what you've seen so far in your studies would be better for targeting this kind of workloads? For instance, the balance between the different units. So can you say anything about that?
Right. So one problem that I'm just going to the right matrix multiplication maybe. One problem that occurred was, for example, with so if you have the high bandwidth memory, you have very also here you have many memory banks with smaller sizes. So this was actually also the main challenge now for all the different memory types I used. Maybe this overview is a little better. Here we have now 32 memory banks, but with a very small size. So actually what this forces you to do is to break down a big problem into a smaller problem. And this is sometimes not that easily possible, let's say, because, for example, now for the matrix multiplication, you need these big matrices. So if you want to calculate not only 1,000 times 1,000 matrix, then you might actually need more than one HBM memory bank, and then place and route might again get complicated because you need to read from different memory banks at once. So this might be a problem for some applications. But apart from that, so also they're actually, from the DSP perspective, the FPGAs come with a lot of DSPs, which allows a lot of single precision floating point computation power, but they most likely suffer on poor final kernel frequencies. So that was also something I actually wanted to emphasize with the matrix multiplication benchmark. So here actually the main problem was that because of this very high parallelism of the matrix multiplication, it was really hard to actually place and route the design efficiently on the FPGA, which resulted in a relatively low kernel frequency. And especially for GEM, this of course reduced the performance.
We had a few more questions coming in. One question by Philip is, how difficult was it to get the PCI Express data transfers working?
Oh, that was actually not complicated at all. So we used a reference board support package that was provided by Intel for this PEC board. And actually it was simple as synthesizing the design with this board support package. And maybe some other thing to note here, if we look into the results, or maybe if you look at the design of the stream kernel, we had this 3 pipeline approach that we always read just one value from the global memory. This does not work well with shared virtual memory, because if we want to utilize the PCI Express connection fully, then we actually need to do both simultaneously, read from the global memory and write back to the global memory. So we need actually one pipeline. And so we could actually do this with our design by just reducing the size of the local memory buffer, so that we actually end up with a single operation here for every of these steps. And then this becomes a single pipeline that does everything simultaneously. So here you have to, if you use shared virtual memory, you have to take different approaches, because you also have to consider this full duplex communication actually.
Okay. I think we have time for a very last question by Tiziano. This question is, are the benchmark implementations differently optimized for the architectures that you have considered?
So I tried to find a design that works well with both, for example, now Intel and Xilinx. And this actually also worked for most of the benchmarks. So for Stream, it works. For RandomAccess, it's the same. For FFT also. For GEM, we needed to actually change the calculation, maybe to shortly go through this. So we have actually in the matrix multiplication benchmark, we have 2 main pipelines. One pipeline just reads 2 blocks of a matrix into the local memory. And then in the second pipeline, we do the actual calculation. And this calculation is fully unrolled. So, and now we have actually the Xilinx and Intel compiler behave there differently. So there we had to actually do different, we had to implement different ways to actually make that work well on both devices, on the FPGAs of both vendors. So for Intel, it was more like a Canon matrix multiplication that works well. And for Xilinx, it was rather the classical matrix multiplication approach.
Okay, thank you very much for the interesting talk. So we can wrap up here perfectly on time and proceed